learning from experts across the ocean.
Welcome to Voice of the Sea.
This time on Voice of the Sea.
So we get to learn about crystals, and you're studying volcanoes on Maui.
I am.
Is that right?
Yes, from Haleakala.
Wow, that's really exciting.
It is.
Can you share with me what you're looking at?
Sure. This is one of the postdocs who just left, went to Maui about 3 or 4 weeks ago, and he actually brought this back from the lava flow that the crystals are coming from. So you can see the green crystals are the olivine, and then the black shiny ones are the ones that I'm studying.
Very cool.
Yeah. And I can pull out some of the crystals, because my project is kind of nice because these crystals are actually weathering out of the lava flow.
So they're harder, and then the rock erodes around them.
Right. So this is what the crystals look like, and they're just kind of weathering out and
No
lying
way,
around.
really?
Yeah. I have a whole bunch of them in the cabinet over there.
That's it's a surprisingly geometric shape with hard edges and angles.
It is. The faces, the crystal faces we call them, are very pretty.
And do you know what it's made out of yet?
These are clinopyroxene, so there's calcium and silica and oxygen, and then iron or magnesium. So
And what are you trying to learn by studying these crystals?
we're actually thinking that they formed from a dendritic growth pattern. So dendrites are kind of this branched tree pattern where it has one main branch through the magma that it's growing in, and then secondary branches, kind of like a picture I have over here. This project stems off of a previous one done on different types of crystals. So these were olivine crystals, but these are the dendrites you can see here. They're branched, and this is a picture of the inside of one of the actual olivine crystals. So you can see all the dendrites that formed on the inside. And a lot of people think that since the crystals are so nice and flat faces, that they grew slowly and kind of like a tree rings in the magma they were growing in. But we're actually thinking they grew from the dendrites. And so we're looking for, in the microprobe, which we can go down and see later, we're looking for elements that will give us this type of pattern in the pyroxenes.
Can you explain again that difference between the crystals forming in a tree-like pattern versus the crystals forming in a dendrite? I'm not sure I said that correctly, but...
Well, it goes back to when the crystal first starts growing, and there's like one atom on a flat surface or another crystal that formed already. And so there's like a bump, and that bump continues to grow without the rest of the crystal growing. So it grows faster than the rest of the crystal, which will give you the tree branched pattern. A lot of people think, though, that with these pretty crystals, it grew in a ring pattern, all at, like, the whole crystal all at once.
I see.
But we think differently. So we're hoping to find the proof, whether or not that's true.
And I see on here this observation, hypothesis, test. Are your studies supporting your hypothesis, or this is actually a different study?
This is a different type of crystal, but the dendrites here would definitely support our theory. A lot of people think that the rounded shape of these crystals comes from remelting of the crystal while it's maybe sitting in the magma chamber still, but we think that this is the final growth outline of the crystal instead of being remelted.
And so that's a novel or a different way of looking at the crystal growth. And what brought you guys to that hypothesis?
Well, It's the last postdoc that was here. He just went back to France a couple weeks ago. He just kind of brought it up he was doing a different study on a volcano, and he had budded olivines. So he had this random hunch, kind of, and he went about proving it, or trying to find evidence for it. And then he wanted to see if the crystals from the same type of magma would have the same type of growth pattern, which is what I'm doing.
Very cool. So can you show me a little bit about how you're researching these crystals and what do you do here in the lab?
Sure. Most of what I'm doing in the lab is just through thin sections. So I use the microscope here. And I can actually pull out one of my thin sections.
And by thin section, you mean a thin section of rock?
The thin sections I've made are just crystal, but I do have some being made that are of that rock sample that we showed earlier.
How do you cut the crystals to make the thin section?
Okay, that's actually around the corner. Oops, this box is empty. So originally this is the saw. It's not put together right now, but it has a blade that goes on the inside, just like a circular saw. And
so you'd put this crystal in there?
Mm-hmm. It attaches to, we have to glue it to a piece of glass first with the epoxy.
Uh-huh.
And it would sit in this holder right here. So the slide you always see thin sections on, it would sit here, and then the saw, just like a circular saw, would cut it.
So it would sit on top of this, it would glue it, and then the piece that you look at is the piece that's affixed to the glass.
To the glass slide, yes. And then once it's cut and we have a flat surface, we put it in, we would put the glass in here so that it's held together, and we would polish it. So this has, I believe it's 6 different grades of polishing, kind of different grades of sandpaper basically. From really rough to get it really smooth and flat to really fine to just get out minor imperfections. And then once we're done with that, we can go over to the microprobe or the microscope as well.
Okay. Do you need your thin sections?
That box is actually empty.
Oh.
So hopefully this other box has them. Yeah, there should be a box that has them. So yeah, this is the piece that gets cut off.
Oh, I see.
So after it's surrounded by epoxy, and then we leave this piece on, which is what we polish, and then what we can see in the microscope and the microprobe.
Very cool.
Yeah. And it might be kind of hard to see because right now they're actually carbon coated for the microprobe. So you have to carbon code them for the microprobe so you get the X-rays that you want to come off. So I'm not actually sure if we can see anything, but we can give it a shot.
And this is a high quality regular light lab microscope, right? We're using light to view the specimens.
Right. Oh yeah, it's going to be really hard to see. Okay.
Oh.
Yeah, I'm not going to be able to see much with these ones right now because they just came off the microprobe, unfortunately. But I can show you a different thin section that...
So this one is just not from your Maui rocks, it's from...
Right. This is just a typical Hawaiian basalt with olivines and the glassy matrix.
And can you explain to me how you know which minerals are which, or how you identified the olivine?
So each mineral has what it's called a birefringence. So when you're in cross-polarized light, each mineral kind of has a different color.
Oh.
So, Julia is actually the mineralogy professor here, and you learn all about the different colors each mineral has, and that's definitely an identifying feature. When you just have plain polarized light, most crystals are clear to kind of a whitish color that you see here, and that's not very identifying. So you have to use the Cross-Nichols birefringence. And sometimes you can use shape too. That's not quite as identifying because a lot of minerals can have the same shape.
But together with the shape and the color,
you can narrow it down.
I'm familiar with polarized sunglasses and that kind of thing. Can you explain to me what's happening with the two different polarizing layers? And
I can definitely try.
Okay.
When you have just the one polarizer down here on the bottom, you have the light. It's polarized in one direction. And then when you put so it's just basically reflected light going through the sample right now. And then when you put the polarizer in, you have light going the other way as well. So it comes up through the sample differently and reacts with the molecules differently in there.
And because of the structure of the inside of the crystal, then you see the
different
colors. I get it.
Yeah.
Cool.
So, yeah, that's basically all up here. I can see what other pictures I have up. And if you wanted to get really technical in identifying like the orientation and the face of the crystal, you can do interfacial angles, which is what we're starting here. You just start out with a picture of the outside of the crystal, and then using like Adobe Illustrator, you can find the angles between like of this corner or this corner here, and that's also distinctive for different types of crystals and minerals and stuff. And then here's a picture of the dendrite pattern that typically forms. So you can see the tree branch. So the main one that grew through the magma, and then it had secondary branches coming off as well.
And where's that crystal? That's one of the rocks that you're studying?
It's the same type. It's also a clinopyroxene, but it's not the crystals from Maui. Unfortunately, we have to find a specific element that will give us the pattern. So like here they mapped the concentration of phosphorus in the olivine.
I see.
And so that's kind of the big thing we're looking for next for my project is what element in my crystals will hopefully give us the pattern like this in the clinopyroxene crystals.
And the clinopyroxene, that's a type of mineral.
It's a calcium-rich pyroxene, which is found in most Hawaiian lava.
And it's characterized, it's normally that black, dark color.
Yeah. Yep. Black and shiny.
Do you know if that is one of the components of, say, a black sand beach? Is that what weathers down to form black sand?
It can be, yes. Like on the Big Island, there's some.
Very cool.
You can also have green sand beaches, which are the olivines.
The olivines.
Yeah.
So we just looked at the light microscope upstairs, and this is the Microprobe. What does that mean?
Well, this will give us the composition of the sample. The thin section slide that I showed you is what we put in here. It uses an electron beam that kind of starts up here to kind of shoot the sample. And then what bounces back is different X-ray. Different X-rays that are different for each mineral. So there's spectrometers, which there's 5 of them on this one, which you can see with the little flags are on each spectrometer. And they'll count how many of the X-rays or that are coming off in the different X-rays, and an amount of X-ray corresponds to a concentration that's in the sample. So the more X-rays you get, the higher that element is in concentration in the sample. Does that
Okay.
make sense?
Can you explain it all again, sort of from the top? So coming through the blue column is an X-ray.
An electron beam.
Okay.
And then what bounces, once the beam hits the sample, what bounces off is X-rays that are different, kind of like, you know, the X-rays we have. And they're different for each mineral that's in the sample. So wherever the beam hits, different types of X-rays will bounce back, and the spectrometers count them in different, based on, you have to calibrate the whole machine based on minerals that have known concentrations of each element.
Mm-hmm.
And so it compares the counts that it gets from your sample, which is your unknown, to samples that have known concentration of each element.
And from that, you can tell what elements are in your crystals.
Mm-hmm. And it prints it out in this big, long Excel spreadsheet.
Very
So,
cool.
yeah.
Do you also get a picture of what your crystal looks like?
You can take pictures beforehand. I have some upstairs of mine, or I'm not sure what this is of, but they're kind of just black and white. You take pictures especially too, so you know where you're at in the crystal, because once it's in there, you don't really know where you're looking at.
I see.
So you can pick it on the screen, which is not up right now, and then you can write it on your picture so you know what matches. And then in your data later, you can go back and say, oh, this point is different from this lighter gray because for instance, it could have more calcium or different element composition.
And the crystals really grow like that, where there's parts of them that are higher in some mineral composition than the adjacent spot.
Mm-hmm. Definitely. Huh. That's a picture of mine.
Really?
Yeah. Yep. So yeah, I took, like, for instance, I would take different points here in the lighter gray and in the darker gray, and then it gave me different concentrations of each element that was in there.
And how is that information useful in describing your crystal?
Well, because of the rim you can see, the light rim, it tells us that at one point towards the very end of formation, the crystals had to have grown slower than originally. Dendritic growth is very rapid, but to get the very pretty flat faces, it must have slowed down considerably. And that's also why you can see the color change, because once it's at its big growth that we see, it's limited on what minerals are left in the magma and what it can take. So it'll have different color, grayscale colors in black and white.
So when you looked at, you made your hypothesis about dendritic growth. Like you said, the crystals have such nice regular shape that people originally thought that maybe they grew very slow. But when you look inside them, or you're seeing evidence of this dendritic growth, but then they did have to slow down to make, I'm sorry, it's probably not a camera question, but I'm trying to understand it. It almost looks like it's supporting your hypothesis about the dendritic growth. If it looks like it grew fast in the middle and then it slowed down toward making those hard edges.
Right. Yes. That's what we're hoping for. That's what we're coming to. So.
How will you know when you've got there? Is it a kind of a thing where you look at enough samples and they're showing a similar slow growth around the edges?
We'll know for, more, certainty when we finish making the element maps. So also with the electron microprobe, you can make just a map of one element. So the brighter the color, you can use like green for instance. The brighter the green, the more heavily concentrated that spot is with, I don't know, like calcium. So hopefully we can find an element that shows the dendritic growth patterns, which would really be like the smoking gun of this project.
I see. And that's what we saw upstairs in the olivine.
Right. Yeah, they had the phosphorus maps. And mine don't have any phosphorus in them, so we can't use that, but maybe another element that's in high enough concentration that we can use.
I see.
And the spectrometer is going to tell you what elements are in there, and you're going to kind of go through one by one looking at those elements for traces of...
Right, yeah. We'll make the map using this, the element map using this, and then we can go back upstairs and just kind of... You can't really see it with the microscope upstairs. It's not something you can see with just the reflected light. You have to use the X-rays that bounce off to see it. I don't know if I can pull up. Okay, yeah, we're not going to be able to see anything on that. But this would increase the magnification, and these ones are to focus the picture. And then these are kind of to navigate the image when it's not running. So when you pick your points, after you calibrate, you pick each point using these ones. So like on this image, it would have a crosshair, and you would drive around to whatever spot you want. And you would push some buttons on here, and it would save that location in the crystal. And when you hit go, it spends however long driving to each location that you picked and analyzing the composition.
And it does that in an automated way.
Yeah.
And that's kind of what it's doing right now.
The fact that the little flags and spectrometers are turning means it's analyzing a spot. You can kind of see the list, I don't know, the list of points that this person picked. And then here's the go button to get it started, and the run button. And then this is just kind of, it's putting out rough calculations right now of the elements and their concentration. And this will tell you the spectrometer that it's using. So each spectrometer has, like, to get really technical, it has a different kind of crystal that analyzes different minerals better than, say, a different spectrometer. So you put certain, like silica, you always want to put on crystal spectrometer 1, because that's the easiest one to use to get the best results.
Can you explain to me what a spectrometer is?
Sure. It has this crystal in it, and there's three main different types of crystals, and it sits there. And the spectrometer is a bunch of different stuff that rotates the crystals at different angles to calculate the X-rays that are bouncing off the sample.
And so when you, on this machine, there are 5 different spectrometers, and each one is outfitted with a type of crystal, and it's specialized in what it's looking for.
Right. So this is the electron beam that's focused by magnets that are on both sides here. And this is where your sample would be. So it hits the sample, and the X-rays bounce into, this would be one of the spectrometers. So it bounces and hits off the crystal, and then it bounces again and would be counted here in the counter.
I get it.
And then this is the stage your sample sits on that you can move using the joystick over there to get to different parts of the sample. The electrons from the beam interact with the electrons of the different elements that are in your sample, and the X-rays are produced that we count to get the concentrations.
The Curriculum Research and Development Group in the College of Education at the University of Hawaii at Manoa. CRDG's training roots go back over 40 years. Through professional development programs, curriculum workshops, research on teaching methodology, individualized school and district training, and so much more. The Curriculum Research and Development Group, improving schools, improving education. CRDG.
NOAA Pacific Services Center, linking people to information and technology. The Pacific Services Center wants you to be prepared for any weather emergency and know your tsunami risk. NOAA Pacific Services Center, enriching life through science, service, and stewardship.
Exploring Our Fluid Earth is the dynamic curriculum developed by the University of Hawaii's Curriculum Research and Development Group. The award-winning Fluid Earth and Living Ocean textbooks are now interactive and online. New activities, updated content, and a teacher community. Exploring Our Fluid Earth is now freely available. Find out more at exploringourfluidearth.org.
The University of Hawaii Sea Grant College Program, helping coastal communities of Hawaii and the Pacific through research, education, and outreach. Serving the community from elementary to graduate students. Hawaii Sea Grant.